Okay, so some rules. So every time I mention a person in this thing by name, they actually existed and were a real person. Every time I say they invented something, they actually did invent that thing. And every time they curse, I have used authentic ancient Greek curses that are PG-13. If this sounds absolutely insane to you, you will understand in 2 seconds. There will be subtitles at the bottom of each slide, generally for if you think a little subject is interesting, you can, go to the Slack channel, find the thing, click the link, and learn more. And this is going to get like kind of really sloppy and silly, sort of a crazy idea that I have never done before. So just sit back and enjoy. All right, so setting the scene back to 330 BC, our location is ancient Greece. This is Alexander the Great, a brilliant warrior and strategist who ascends the throne basically at age 20. By age 30, he conquers more than like most empires ever did, and names a bunch of cities after himself, and then just like dies of disease, which is classic. So the yellow circle here is Alexandria in modern day Egypt. And so Alexandria became an extremely rich city that was a hub of trade and knowledge. And this was a time of great philosophers and great scientists, right? So Socrates, Plato, Aristotle, right? And the story isn't necessarily about them, but it's about where their work ended up, which was the Library of Alexandria, right? Before Google and before Wikipedia, this was basically the biggest collection of human knowledge ever, right? There was like 500,000 books in here. And this was at a time where books were written laboriously by hand, were extremely valuable, right? Most people couldn't even afford one book, let alone 500,000 books. And one of the ancient world's most influential sources of information, was this place. And works that were stored here and were written here influenced even, the Renaissance in 1,000 years later. So this is the story of four grumpy ancient librarians who changed history by inventing concepts that we still use today. So phase one, humble early beginnings, right? So here's a day in the exhilarating life of a librarian. Top-down view. The gray things here are shelves, right? We're in a little room. The thing at the top is the librarian's lectern. The librarian happens to be sleeping at this point, right? New customer comes in. They're like, hast thou the plays of Aristophanes? Because, I don't know, ancient people spoke like that or something. And then so the librarian goes around, looks at the first shelf, whines a lot, arrives at the shelf. Now, so this is just like a bookshelf. And each one of these brown things is like a book, but, it's a scroll that's been rolled up and put into a case, which is, a book technically. Okay. So what he has to do is he has to like pull one of these out, like remove it from the case, look at what it is, and then place it back. It's like, oops, it wasn't this book. Well, pull out the second one. Look at what it is. Oops, it wasn't this one either. And just keep doing this over and over for every single book in the shelf. So, okay, it takes a little bit more looking. And then eventually he finds it, brings it back. Boom, we're done. Okay, so we have about 500 books in our library, right? And it took us about 5 minutes to find a given book. So it's a little bit annoying, but like not terrible. So, but what happens, if we change things a little? So some years later, the king acquires more and more riches and is keen to show it off, right? So what better way to do that than buying more books? So now it's the same thing, but a lot bigger, right? Our patron arrives. We just have to walk through way more shelves before we find the thing that we need. So now we have 10,000 books, right? Like 20 times what we had previously. And it takes us like 45 minutes. And only because we got lucky, right? Like we found it halfway through, but it could have been like at the very end and we would have spent all this time. So where did we spend our time right now? We spend it mostly pulling out every single book in every single bookshelf, which is just, takes forever. And then just wander to each shelf, not necessarily knowing where you're going to actually, which shelf you might find the book in. So this is pretty terrible. So, our new librarian decides to institute a bunch of reforms, right? So problem number one, pulling out each scroll from its case and looking what's inside is a huge pain in the butt. So Uh, oh, so what you do is you attach a dangling tag on each book and write the book name and author on it. And so for the first time in history, you invent the concept of metadata. And so what this means is searching a bookcase involves no pulling out of books, right? You can just look at the tag without removing the book. The cons are, you just have to write a tag and attach, but it's kind of worth it. It pays dividends over time. There's your little books with the little tags. Okay. Problem number 2, old librarian used to know where everything is, but now it's just too big for that. So solution, you split the library into different rooms based on category, right? The benefit is when you're searching for a thing, you only have to search within that category, which is really nice. The cons is, okay, you have to like arrange things, and when new books come in, you have to put them into the correct room, but not really terrible. And then third thing, right? Even with rooms, there's still too many shelves per room. So what if somehow everyone agreed on, where everything should be? Well, there is actually a thing that's a common agreed upon ordering, which is the alphabet. So for the first time in history, you invent alphabetical sorting. So you sort all your books by author. And the benefit is that you can guess approximately where a book is only by knowing the name of the book. The cons are you have to like move and shift stuff around, and we'll talk about that a little bit later. But so putting it all together, right? Take 2. Let's try this again. So person comes in and they're like, Sappho's poems, where are they? And you know that poems are literature. So all I have to do is like walk straight to the literature section. And then, all the shelves here are organized from A to Z, right? If the first one is A, the last one is Z. So S is probably somewhere near the end. You go there, you find it, right? You're like at the shelves, right? You find something with a P that's too early, right? So then you look at, a little bit further, you find something with an S, SY, that's too late. R, that's a little too early again. So you do this like bouncing around back and forth motion, right? Until you find the book. So this really helps find things because we only checked a handful of books out of like 2 entire bookcases. So saves a lot of time. Now, we had 10,000 books, right? Finding time, we went from 45 minutes all the way down to 2 minutes. So that's really good. And where do we spend our time? Right, walking to the correct room, walking to the correct bookcase, bouncing around the shelf, kind of reading tags. And that's pretty great, right? Like even better than the smaller library ever was, which is awesome. So phase 3, right? Now we want to be a world wonder. So the new king decides that he will build this thing called a museon, which is a temple to the muses. It's the equivalent of a modern research institution, right? And if the word sounds familiar, that's where the modern word museum comes from, even though it's more like a university. But anyway, in it, he decides that he will put the largest library the world has ever seen. So to fill the library, the king sends a book acquirers abroad to book fairs, right? And then he decides that he's going to loan books from the Athenians for money, but then steals the originals and sends back only copies. And then later the Athenians starve in a famine, and he makes them sell their remaining books in exchange for food. And then he invades some nearby lands and loots their libraries for even more books. And even ships that come to his own harbor, he makes them give up their books to be copied, right? So he's just like completely obsessed with just books, acquiring more books. So you wake up one morning and animations, hello? Oh. And there are 300,000 books, and it's your first day as a new librarian in charge of this hot mess, and you have to deal with it, right? So you have 300,000 books, and it takes you about 15 minutes to find a book, right? And you spend a lot of time now walking from one building to another because you just have so many buildings now, right? Once you do that, walking to the correct room is not that bad, but you still have to bounce back and forth in bookcases, and now there's way more bookcases, so that also takes a bunch of time. So just leaving the lobby to walk elsewhere is like the biggest portion. So can we do better is the question. Well, here are some problems. Problem number one, it would be cool to know exactly where a book is without bouncing back and forth through the shelves, right? If we could somehow know that. Problem number two is if the library doesn't have a book, you still have to walk all the way to where the book should have been to see if the book is there or not, which feels a little bit silly, right? So one day, our librarian's wandering through the stacks and they're staring at the shelves and the tags, and they notice the tags themselves and they go, Eureka! They scream, referencing an ancient Greek inventor that won't be born in another 100 years, because they have an idea, which is that they will copy all of the contents of the tags and turn them into a book, right? So it's a book of books, and this is a little bit what it looks like, right? So it's like a little table. So for each row, you have an author and then a book that they wrote, right? So those are the information from the tag. And then on the next bit, you have kind of like where that book should be. So the pros here is reading a book is a lot faster than wandering through the halls and going to different buildings. The cons is that, it might take up a lot of space depending on how many books we have and how complicated. And also the scribes have to make inscriptions, in the index book, basically every time a new book arrives. But we'll worry about that later. So now visually, I've just decided that the index is going to be a green hexagon. I don't know why. I didn't have a better symbol. I'm sorry. So we have even more problems. About half of all the patrons want the same 10 books, right? Like, I don't know, Twilight or something. You spend all this time walking from building to building to the same few shelves that have these same books. And it feels especially silly if you walk all the way to a shelf, right, to drop off a book, come back, and the next patron just asks for the same book again. And then you have to go back to where you were. And that's just really absurd. So what do? In the lobby of our library, we can have like 100 most popular books shelf, right? And the pros are for half of all the patrons, you only have to walk in the lobby. That's like super awesome. And also dropping off a book is faster too. Just drop it in the popular shelf and not all the way to where it's supposed to be. Now, the cons, you always have to check the lobby first, before you check the main sort of stacks. But, that's not a problem. That's easy. Okay, so putting it all together, what does this look like? So case one, popular book, right? Patron arrives. We have a popular book section in our lobby. We kind of walk through. We find the popular book. Give it back. You're done. So not having to leave the lobby at all was our goal, and we succeeded. That's awesome. Saves so much time. Case two, what about an unpopular book? Well, okay, so patron arrives. You kind of walk through the popular book section, but you can't find it. So what do you do now? You consult the index. So in the index, it tells you like the exact building, room, and shelf to go to. You walk there. You walk there? You walk there. And you walk back. It's time consuming, but it's as good as it gets. Case number three, what if it's like some book that we don't have? Then the patron arrives. Now it's not in the popular book section. Okay. Then we check the index, but in the index, we don't find the book. So we don't have to go all the way down to the buildings, right? We can immediately tell the patron, hey, we don't have this. Goodbye. So, okay, 300,000 books. Now we're down to anywhere from 1 to 15 minutes, right? Maybe average of 5. 1 is for, if it was a popular book, 15 minutes for if we had to go all the way down to the stacks, but, a big improvement. So now what? So now the problem that we said we would deal with later, right? While improving one thing, we've kind of ruined the other, right? So here's, your king brings you a new book. And so what are you going to do? Well, you attach a new tag with the author on it, right? You go in the index, add the book to the index, right? So now you're in the library and you have to go all the way to where the correct shelf would be, right? You arrive at the shelves, you have 2 books to place. So you place one book, right? But for the second one, oh crap, there's no space left, right? So what do? Well, you got to like shift all the books around because everything has to be in sorted order, right? To make a little bit of space. And then you plop your second book, right? And this is just really annoying and really time consuming. So what can we do about it? Well, is there a way that maybe we can rearrange everything to kind of better suit our workflow? Well, here's an idea for a new method of handling incoming books, which is a cart with wheels. So newly acquired books sort of appear slowly until the cart fills, right? And then you take the cart, bring it to building 1, and drop off only the books that should go in building 1. Building 2, drop off only the books that should go in building 2, and so forth. Building 3, I guess there's no books for building 3. Building 4, you drop the remaining books off. Okay. So instead of making 100 individual trips for every single book in the cart, we did one trip, dropping everything pretty close to where they should be. And this is really good, right? So laziness is good, right? What we'll do is we'll wait till everything piles up in front of the buildings, and then, building 2 is approaching like a massive pile. So now someone from building 2 picks the books up and actually bothers to put them in the right place, right? The only thing is, if you do this, then if you're looking for a book in that building, right, you got to first check the entrance before checking the main room. But that's also, it's worth it, you know? So, okay, like that's kind of like how we play around with these things. Now, let's think about how let's talk about modern databases and how they would have worked in the ancient world, sort of. So MySQL or Vitesse, the sort of main general use case, like most of the time, fetch and return individual rows. Once in a while, we might modify some of those individual rows. Now, if you look in the internals of MySQL, you'll see something complicated like this, which looks really intimidating until you realize that this is the same thing as this, right? So you have, some shelves. The shelves are grouped in rooms. Within a room, things are organized, and then, in a different room, they're also organized separately. And then those rooms built together, and you have this sort of like upwards going tree structure. And, the library design that we built is very similar to what MySQL uses to store data, minus the cart bit. But and that's basically the core of it, right? We didn't really talk about concurrency and transactions, and don't worry about those. There's more optimizations and details, but the core is this. Okay, what about like Snowflake, which is a different sort of database? So the main use case here is like it's an analytical database, right? So let's say we had to worry about the king's taxes, right? How much did the XYZ region, of Egypt provide in taxes this year? You got to like go and find all the right shelves, for that region, and then sum all of the taxes in those shelves, right? So it's a little bit different. Like there's very little need to look up a particular item, right? It's more about calculations across the entire room, right? We've got to look at everything in the shelf and add things up. And there might be ad hoc queries, right? You don't know what question the king's going to ask up ahead, right? Unlike MySQL, where generally you have a small, well-optimized set of queries. And also, the taxes are updated once a year and very infrequently, but whenever it's done, a ton of data is loaded all in one go, right? So specifically, the fact that you have to do calculations across large, regions, and it's hard to know, what queries we'll be doing, right? That means that indexes are generally, sort of a waste of time. So they come up with a different way of doing these things. So on top of every bookshelf, they store these values where they store basically kind of like the minimum and the maximum value for each bookshelf, right? And also some other aggregates, how many things are in here and what's the total. So if you come with a query that says, okay, get me the total taxes where the name is greater than, Stavros, then what you can do is you can just skip entire regions because you know that in the first bookcase, the maximum is F. S is bigger than F, so don't need to look at this one. The second one, it ends with Stavros, and we want greater than that, so not that one either, right? So it's only the third one, and we know that we want everything up to the maximum, right? So the count is already there, and we don't even have to calculate everything, right? So there are cases where sometimes we have to dive into things, but if you have like hundreds and billions of these bookshelves, then this sort of data skipping thing makes things really fast suddenly. You're spending a little bit of effort like pre-calculating these things and storing them, right? But it has a huge benefit. So what about Elasticsearch, right? So what if searching for books themselves is not enough and you want to search for the contents of books, right? So which books contain the word blah? Well, animation problems. So being able to find stuff within books requires the scribes to actually read through them first, right? You have some special kind of scribe, right, who arrives and says, okay, well, I've read through the whole book. The word magic is on page 23. And then they add that to a special index called a position index. And you'll see that in a second, right? And then they read another book and they say, okay, magic also appears here on 2 different pages, and also the word witches appears. So then you put all these words together with the positions in a table that looks like this. So you have a word, right? And then you have the book that it's in, and which page and which line it appears in, right? The books, we have a special index already for how to find them, but basically now you have an index of words, so you can search things by word rather than by author. That's the core idea behind Elasticsearch. I am realizing that I actually skipped a slide. Whoops. Okay. Well, what about Kafka? Well, imagine that we have, the king's mailroom. It's a really big mailroom with long tables. The gray things are tables. When the king makes decrees, we place them in order on the tables. And, when a table fills up, right, we kind of move on to the next table. The room is a fixed size, right? If we fill up a room, then we just kind of remove stuff from the earliest table and put it back again. So when a messenger comes in, they remember the last decree that their boss received, right? So they received 19, so then now they want 20. So they look in the index, where's 20? The index says, oh, it's on table 2, right? And then they find 20. They look at the message, make a copy for themselves, and then get the heck out of there. And that's pretty much the core idea, right? You just do this with hundreds of messages and hundreds of messengers at the same time. And, if the messenger's waylaid somehow, right, the boss can always just send a new one with the last decree number that they know that they have received. That's pretty much the core idea behind Kafka. What about HBase? Okay, I don't have, unfortunately, great animations for this one, but it's very similar to the book cart idea, right? Remember, we have a cart that we like slowly pile up things out of order in, and it's like nearby in the lobby. So instead of dropping books off in a pile in front of a building, what you do is you leave the cart and you just bring more and more carts. At some point, you have like 2 or 3 carts in front of the building. What you do is you combine those carts together, sort the things in there, and put them in a shelf. That's sort of like the general idea behind an LSM tree, which is, what HBase uses. Okay, so conclusions, right? Every vendor will claim that their database can do every single thing, but doesn't mean that it's optimal to do so, right? There are fundamental trade-offs at play here that stem from kind of like the core way that the data is organized, right? So for example, Snowflake versus MySQL, they both use SQL. You can represent the same SQL schema and do the same SQL queries in both, but they will behave like quite differently for the exact same workload. So this is a thing called the RUM, read update memory conjecture. So what this says is, if you want an upper bound on 2 of these things, you must accept a lower bound on the third, right? So Either you have something that's good at both read and update, but it takes a lot of memory, or you have something really good at update and saves a lot of memory, but is really slow to read, or something like that. There's no free lunch is the idea. Now, let me explain to you the core constraint behind all these databases. So meet the memory hierarchy, right? So at the very top, you have, your regular old computer CPU. It's a processor. Processors are really fast these days. Right below, you have little bits of memory that don't matter that much, but live within the CPU. Right below that, you have main memory, which is kind of what we think about as memory. Right? And right below that, we have secondary storage, which is like hard drives, SSDs, EBS volumes, that kind of thing. So as you go up top, things get faster, but also more expensive and smaller, right? And as you get to the bottom, they get larger and slower. So now here's the thing. If you look at these numbers of how long it takes to access one of these things, right? There's a little wall here where everything suddenly takes 10 times more if you have to go to main memory, right? This is equivalent to the librarian's desk versus the librarian's lobby. So, bit of a hit, but not so bad. But then here's the second wall, right? Which is between the library lobby and other buildings. That's a multiplier of 1 million. That's not a typo. That's exactly actually what it is. So these walls are the sole concern that dominates almost every single design decision, often more than like big O or algorithmic complexity, at least in database applications. So this is why, using an optimal index, right, the green hexagon, will give you many order of magnitude boost because it minimizes the amount of accesses you do beyond the wall. This is also why a small data size will hide a multitude of sins until your data stops fitting in RAM, and then boom, performance falls off a cliff, right? Like we hear a lot of, it was working fine, and then suddenly it doesn't. So this is the main reason why we do all this data structure jiggery pokery, is to minimize accesses to slower storage. So do I mean, what I want you to get out of this is that data structures aren't necessarily static things with strict definitions that you memorize, from a Wikipedia article for your next programming interview, right? They're just a collection of tools and concepts that you mix and match to solve specific problems given specific constraints. Now, do I mean everyone go implement your own data structures and databases? No, leverage existing implementations. Implementing is also hard, but it's a pet peeve for me when I hear that the book says that, data structure XYZ is exactly like this. And in reality, if you open up 8 different implementations, you'll find 8 different versions of, what's allegedly the exact same thing. So why learn all this stuff? If you learn how your data structure or data system organizes data, you can use it more efficiently, often by orders of magnitude. So this isn't about memorizing data structure trivia, right? It's about, being able to leverage and use things better. So there are very few real world systems that use only one of these data structures anyway. Right? Here's MySQL using a bunch of them all at the same time. They often use many in conjunction to try to mitigate the weaknesses of the core structure that they use. So the RUM conjecture still applies, but and then the combined performance characteristics of all those things together result in something of a hybrid. And it just turns out that there are actually many little design primitives that you can use, right? That you can put together in many different overall shapes, and you can combine them in arbitrary ways to come up with many different data structures, right? So this is sort of like a periodic table, and every little gap that you see here is a data structure that hasn't been invented yet. It actually gets worse. If you start thinking about parameters that can be tuned, right, it's actually a continuous surface of adjustable trade-offs, right? You can think of these things as design continuums. So on this chart, on the y-axis, we have lookup cost, and on the x-axis, we have update cost, right? So on the left, we have, a log, which is literally just adding stuff at the end, which is, really easy to update, but you have to go through the whole thing to find something. And then on the right, we have something that's really hard to update, which is a sorted array. You have to insert things in the correct place, but it's really fast to look up and as structured as you can get. Turns out there's a lot of other potential structures in the middle and all the way throughout. So this is why a lot of the research these days is going towards what's called adaptive data structures that combine multiple elements of these things, or morph live based on workload changes, or behave sort of locally differently in different regions of the data, depending on how the different regions are accessed. So the idea is to try to squeeze the RUM trade-off curve for everything that it's worth. And, these are in research databases and are leaking into like actual databases. But anyway, next time you get annoyingly vapid interview questions like, how many types of tree data structures are there? It could be like literally infinite. And then, how's a blah, blah, blah tree different from a blah, blah, blah tree? You can be like, they're merely the manifestations of the same underlying concepts. So here are the takeaways. Databases are designed around minimizing access to slower storage. Trade-offs regarding storage define performance characteristics of a database. Reject prescriptivist labels on data structures. Recognize your requirements and see what will fulfill it. The way you arrange things should be a function of the way you intend to use those things, right? Even if you don't control how your database works, you can control how your data is structured within it and across your systems and apps. And also databases were invented by ancient librarians, I guess. And remember, there are no data structures, only anarchy. Thank you. That's all. Whew.